Okay, great. Thanks. Thanks for the invitation. I'm really glad to be back. It's been, Shiraz reminded me, 8 years since I was here for an extended period of time. So I guess this is not necessary for this audience, but I'd like to say just stop me whenever you need to, and I will try my best to answer your questions. And if I can't, I will do that by lead. So the broad theme of what I want to talk about is constructing static amplitudes in various fun ways. And this is work I've done with all of these wonderful people. Importantly, my advisor, Henrietta Elvine, two of her then graduate students, so Callum Jones, who's a postdoc at UCLA, Marius, who was a postdoc at Norita, Laura, who's a postdoc at ETH, and then there's Yaroslav Trinka, who I started working with when I went to Davis. Three of his graduate students, Min Chantal and Umut, and finally Carol Kapp, who's faculty at Charles University. So, wouldn't have been possible with all of these people, and please check out our papers if you're interested. So, okay, good. I wanted to actually put the QMAP logo up here, and as you can see, I'm really repping UC Davis. And the reason is because the first talk will deal with this second-most ring, the second will deal with this innermost, and the third will deal with outermost.
Shruti, I noticed you said the slides say 1 to 50. I suspect you'll only get through the first talk.
Okay, the first 10 are right ahead of me. We will find out. But okay, let's just start. So the first few slides, as I said, are very easy to get through. It's that what we're going to be interested in is constructing static amplitudes in quantum field theories. I will only be in 4 dimensions. I will mostly only be dealing with massless particles. So in case I don't tell you it's massless, it is massless. If I tell you it's massless, it's not massless. In this talk in particular, we'll be talking about Born-Infeld theory. And we'll be looking at these various methods. In particular, we'll truncate the non-supersymmetric part of Born-Infeld, but we'll use the fact that it is a consistent truncation. We will use some amount of non-linearly realized symmetry because these are brane theories. And then finally, the real symmetry that we want to concentrate on is this electromagnetic duality, and I'll tell you exactly what that is. Good. Okay, so usually this is what we're thinking about. There's some interaction potential, there's an in state, there's an out state, and then the S matrix element that's related to this in state and out state is called the scattering amplitude at endpoint, and it's fully governed by what states I'm scattering to which states, and then exactly what this potential is. So usually you'd write down a Lagrangian, you'd extract the Feynman rules, you'd put them together in as many ways as possible, you'd sum over all of that. And these steps have different levels of difficulty. So to give you an example of how the levels of difficulty work, if you look at just QCD, so actually, okay, I say QCD, but this is just Yang-Mills. And I'm looking at this process where 2 gluons are going to 4 gluons. And I have, let's say, all of them of the same helicity. So, so here you get 120 Feynman diagrams, which is not great. And this is the original 1985 paper by Park and Taylor. And I just want to emphasize that, actually, ignoring the first page, this is the answer. It's not the computation, it's the answer. And then very soon after, just a year after, they simplified it to this. Okay, so this should really give you a sense of why you shouldn't be using Feynman diagrams in every single static amplitude computation, because this seems much, much simpler than what I showed you on the previous slide. And the reason for that is because Feynman diagrams individually are not gauge invariant objects. And so you're summing these non-gauge invariant things into something that is gauge invariant. And it's like doing a jigsaw puzzle, but what you should be doing is the easiest jigsaw puzzle in the world. Right? You're supposed to take things that are gauge invariant, add them together, and get something. I mean, so you shouldn't be using non-symmetric building blocks. You should be using building blocks that they themselves satisfy the symmetry so that you would guarantee that what comes out satisfies this.
So theories with no gauge invariances Feynman diagrams are as efficient as you can get?
No. But in theory, there's no symmetry, probably.
Okay.
But it doesn't have to be gauging. So it could be something else.
Okay.
But you need that something else, otherwise. Okay, so in particular,
In the previous slide,
yeah.
you had internal color, flavor, and gauge. Where color and gauge separate?
Yes. I mean, it depends on what you mean exactly by gauge. I guess when I say color, I mean what is the color group? Is it SUN or is it UN? Like what is the thing? And when I say gauge, I mean that you can do this some transformation that leaves the action. Yeah. Yeah. So you could have like a massive colored vector
Okay.
where you, yeah. Yeah. I mean, it depends on exactly how you use these words.
Okay. Yeah,
So I try to be specific. That's all.
Okay.
So in the case particularly of Yang-Mills, we just quickly go through how the various things constrain what you're allowed to have. Right? So you have obviously your Lorentz invariant. So you can only build things out of Lorentz invariants. And so those will involve momenta dotted with momenta, momenta dotted with polarizations, polarizations dotted with polarization. You have the Poincare group, so you have to conserve momentum. So you're not really a function in the strict sense because you have an amplitude that's multiplied by this Dirac delta that's sitting on it, right? And if it's supersymmetric, which often Yang-Mills is in these circles, then it's a super momentum concept. So the next thing is that you're dealing with something that has these color, whatever you want to call it, that they transform under some SUN. So the full amplitude has all of these traces of generators sitting out in front. So often what I'm going to do is pull out that trace, which I can always do in this single trace way at leading order. So at tree level or at large N. For now we're dealing with tree level. So I can pull this out in this way. Traces are cyclic. So you can always fix one of these and then you sum over the orderings of these. Okay. So this means that while this is a fully Bose symmetric amplitude, the thing that it multiplies, so this object over here, the partial amplitude, is ordered. Okay, so that's the color ordered object. Finally, we use the fact that it's actually Yang-Mills, not some random theory, by saying that the coupling constant is dimensionless. And so the actual kinematic part of my amplitude has mass dimension 4 minus n, which is just true of all amplitudes in 4 dimensions. Okay. So the last two conditions will be locality and unitarity. Just like gauge and color, these people use these words a bit interchangeably. So I usually mean locality to say that there are poles and branch cuts in the correct locations, and unitarity to mean what happens when you're on those branch cuts or poles. In particular, if you're on a pole, you have to look like product of lower point amplitudes. If you're on a branch cut, you have to look like product of lower point amplitudes, but in a slightly more involved way. So it's the discontinuity across that branch. Okay, good. So for that nice formula I showed you, this one, the Park-Taylor formula for MHV Yang-Mills amplitudes. This is all you need to fully determine. There's nothing else you can write down. It has to be the Park-Taylor. So you didn't have to do the Feynman diagram calculation. You just had to write down these conditions. So that's the only possible structure I can write down that satisfies all these conditions. So that's so this is kind of the philosophy of everything we'll be doing, which is you try and write down these conditions, and after you have these conditions, there's nothing else it could possibly be. Okay. So,
I'm sorry, this will be a large part of what you say, but okay, I don't know anything about the subject, but Park-Taylor had some supersymmetry or something, or I mean, is it always the case that these conditions will just allow you to get back to the answer, or is it okay after the fact you could understand it? I mean,
so it's true for all Yang-Mills amplitudes.
Okay, just these things
At
have
tree
a
level.
unique answer.
At tree level.
At tree level, okay.
At
But
tree
then you have
level.
no branch cuts, right?
Yeah, but you have poles,
You only go.
only poles. But all endpoint Young-Mills amplitudes, all of those conditions are enough to say what the amplitude is.
And just,
not-
sorry, once you start getting branch cuts, you have.
So this talk is going to be made, well, okay, till slide 27 will be at tree level, but beyond slide 27, we'll be talking about one loop. And that's precisely the idea. What can you do when you have a branch cut? What can you do? Yeah. And there it will really draw from the tree level story because you basically want to cut the loops up as much as possible into as many trees as possible. It says that right here. Okay, so using trees to determine loops will be this lecture. The next one will be about the double copy, and then finally it will be about positive geometries.
But just following up on Sandeep, if you want to fix loop levels, unitarity gives you the non-analytic part of the loop level.
Yeah.
But at loop level, you can always add extra tree level counter terms.
Good. Yeah.
So presumably it's some behavior of the scattering amplitude at infinity that would be the hope for fixing these additional things.
Good.
Like Rayleigh behavior, for instance.
Yeah. So that is one possibility. And for us, what we will be using is the fact that we know that Born-Enfeld comes from some brane construction. And so it has to satisfy like T-duality and some low energy theorems.
Right.
And so you can use that to fix then this other what we call rational contribution, which is the part that doesn't diverge. Yeah. So the finite part.
From analytic part.
The
Finite but analytic.
yeah, finite.
Every
but-
non-analyticity is fixed by the unitarity.
Yeah, exactly. Yeah. Analytic, but may or may not be local, which is then the question of whether some symmetry is anomalous or not. Yeah. Okay, cool. So Born-Enfeld theory, as I said, is a brane model. So it originally actually Born and Enfeld came up with this model in a fully different context, which was to fix the self-energy of the electron problem, and it didn't work. But then the name stuck because the model was then sort of rediscovered, I guess, as the low energy dynamics of an constraint. So this is in these papers, right? Flatkin and Seiken. Polchinski wrote out more of the terms that are the action. But yeah, so this is the Born-Enfeld action in 4 dimensions. So in 4 dimensions, what you're thinking about is the space filling D3 brane, and actually I don't know why I drew this, but you don't have this scalar modulus if you're thinking about it as space filling. So you just have the wiggles of the string on the brane, and that's the field aiming. Okay. So this is just a fully vector action. And I want to emphasize that this part of the action itself is normally what you'd call higher derivative, right? Because you have, all of these terms, this is a 4 derivative term. I think alpha prime to the n is probably something like 2n plus 2 derivatives. It scales with n is the point. So each n point, you have a different number of derivatives. But the number of derivatives is fixed by the fact that you're going to have the same coupling constant in this first line. So when I talk about the Born-Enfeld effective field theory, I'm talking about even higher derivative terms. So instead of having f to the 4, d2 f to the 4. So these are the kinds of terms I'm not going to be dealing with today. I'll be talking about this. Just higher derivative, but I'm not going to call it higher derivative.
Velocity powers, not accelerations.
Exactly. Yeah. Yeah. So it's just it's a supersymmetric analog of just a brane position.
Sorry, Shruti, just one thing from your previous thing.
Yeah.
You said that every tree level amplitude in the angles can be determined. Is this basically
This is
BCFW?
BCFW. But it doesn't have to be BCFW. Actually, you can do. The angles is great because you can pretty much do any shift and you can get the answer as having to be Young-Mills amplitudes. You can just shift every single line instead of doing 2 lines, and normally you're doing BCFW and it would still work. So BCFW is Brito-Kirchhoff Penning with them, and we have this construction of Young-Mills amplitudes at tree level, mostly at tree level it works. And it involves complex shifting 2 of your external momentum. But actually, if you were to instead complex shift all of them, it would still work. for Young mills. BCFW also works for gravity, and there you're way more constrained.
And is it right that BCFW works less well for pure scalars? Because it doesn't
if you're thinking of like
infinity.
5-4.
Yeah, right.
Yeah. If you're thinking of 5-4, yeah, it's just the Feynman diagram expansion.
Sorry to be so remedial, but just, so is the statement that if I just pure glue Young mills, I have to write down an amplitude at tree level? I can just write it down from these things. I mean, just take a piece of
Yeah.
Wow. Arbitrary endpoint.
Yeah.
It gets
Thank you.
harder and harder when you're going away from
MHV.
MHV.
It gets harder and
But
harder.
it's all in principle. Right?
But it's all in principle.
Much less work than the Feynman diagram.
Yeah. Yeah. Just even in terms of number of diagrams, but also the complexity of each of the diagrams.
And then one last thing, suppose you had fermions, okay, no scalars. Is that still true? Could you do it in QCD?
So I think when he said scalars,
Just
okay, I mean,
Oh,
maybe I
supersym-
don't want to assume, but
supersymmetry.
I think you meant like 5-4.
Yeah.
So not the scalar that sits in n equals 4 super hard.
fine, but
Yeah.
say just real world QCD with fermions and can
You
you
can
just
do-
write down all three? I'm just curious, I don't know anything else.
You can do
With supersymmetry or without?
Without.
I don't.
You can do for a few lines. So definitely 2 lines you can do.
Two in
uh,
two.
Yeah. No, 1 in 1.
Okay, self.
So, yeah. Yeah. Well,
Okay, something. Okay.
yeah.
So what's the reload diagram for that?
Self energy.
That's a reload.
Like content.
No, you exchange photons.
Yeah.
Exchange photons.
Like content. Stack.
Two.
More than two going.
But then also,
Two.
He's talking about.
no. Okay, I don't know. Okay.
Okay, never mind, it's an aside.
No,
I'm just curious
like
because
this
that's.
diagram, for example, except with as many gluons as you want.
That's what you
This is 1 in 1 out.
One in one of the fermion.
1 in 1 out for the fermion,
Yeah.
as many gluons as you want. Yeah.
Can you just write this down?
Yeah.
That's
Yes.
pretty impressive.
And sorry, just one last thing about this, just to
Yeah.
jog my memory. BCFW required that the amplitude after you did the analytic continuation died off at least like 1 over S. Or 1 over S squared?
Yeah.
Okay, 1 over S squared. Okay, and in Young-Mills that was just automatically true, is this right?
Yes.
And but for scalars with contact interactions, that was not automatic.
Yes, that's right.
So, yeah.
Yeah, so we'll look at an example of a recursion relation, not BCFW, but it's the same general principle where you do this, you introduce some complex parameter and you use that to somehow exploit the locality of that, of the amplitude that you're constructing.
And that's because you could, for a scalar, just add a contact interaction. Is that right?
Yeah, that's so okay. I mean, basically, right? If you're looking at any amplitude, you have an, and that's going to look like something with poles or something without poles. I mean, this is not a deep statement, but that's the structure. And in principle, this part you can always figure out. As long as I write down something that factorizes correctly, that's the pole term. Right? So this is fine. So it's just a question of what can I write down without poles. So that's either a question of just mass dimension. So in the case of Yang-Mills, there's just nothing I can write down. There's no contact contribution I can write down. The Yang-Mills is in that sense trivial. Because people are wild to figure it out, but it's in that sense trivial. But as Shiraz says, if you have a scalar, or you have some high derivative term like this, it depends on what symmetries, what you can allow. So then, yeah.
Okay, thank you.
Yeah.
Thank you.
Yeah, we'll see an example.
So it's somewhat tangential how did born and land on this particular theory out of all these possibilities.
Ooh.
Just in case.
We just write down square root 1 minus p square.
But actually, that
What's the
might
big deal?
be.
That's what you would write. I guess.
No, actually, maybe that is what they did. I don't remember originally how they.
It's-
But that's most natural once you know TV.
I agree with you.
So, okay, to answer the question slightly differently, this is not the most general thing you can write down at this order in derivatives.
Yeah, as you mentioned.
No, even at this order in derivatives.
Trace f to the 4.
Yeah, for example. Yeah. So, I mean, these are extra. I mean, these are the higher dimensional.
Okay.
But if you look at just this dimension operator, you can write down
Index
what.
conventions can
Yeah.
have different.
I mean, one trivial way of seeing this is that this and this didn't have to have the coefficients be related in this way. Just have a few. But one thing that Born-Feld has is this property called vacuum birefringence. Basically, the polarizations have the same speed in vacuum.
Oh,
So maybe that's the only thing that you can actually add to Maxwell theory because you don't want it to have vacuum birefringence. Sorry, it doesn't have vacuum. If I'm remembering the definition of birefringence. Yeah. So that's quite a special property. I have actually very little idea how that's related to any of the other properties in Born-Feld. But that is one of the properties. So maybe that's how they fix it.
Thanks.
Okay. Cool. Okay, so
So what was the question about the black terms as against the red terms when dwarf?
well, one answer is that that's the leading order of action. So that's the square root action. This one.
Leading in what?
Leading in derivatives or in coupling terms. Yeah. Yes. So you would have some brain tension or some like coupling constants sitting on it, right? And these would all be subdivided. So for example, this is f to the 4 and this is d2 f to the 4. So it will be circles.
Thanks.
so I'm really sorry, Shuri, I will stop after this, but yeah, just, I would have thought this the speed of propagation is determined just by the quadratic in vacuum. So in this case, it's just f mu nu, f mu nu.
I mean, it has a lot of high derivative connections. I don't know if that's true.
But if it's just speed of propagation, it's just quadratic, right? Higher derivatives you can have.
Yeah, but they'll have some that will correct the speed in some way.
Right. So were there higher derivative terms at second order, at quadratic order? In the red, I see only.
Okay. I think there are not.
There are not.
There are not.
So-
But okay, so to be clear, these will never appear in the original Born-Feld action.
Right.
It's
So,
just the square root one.
so I'm just wondering if the speed of, if maybe I'm understanding completely wrong,
Yeah.
but if I'm just looking at linear propagation,
Yeah.
the speed of propagation then is determined just by quadratic terms, and it seems to me that you're saying that all theories with just f mu nu have the same quadratic term. So it's birefringence. I'm straight out.
Sorry, why can't you like look at self-corrected property?
Yeah.
Why do you want to look at them?
I thought we were doing 3 level, but
Okay.
Oh, okay. At 3 level, yes, you're right.
oh, you mean once you take loops into account? That's what the statement was about.
I think that was the statement that at least at one loop then happened.
One loop, right? Fine. Then I'm happy.
But yeah. But I don't want to actually come into that because I've not looked at that birefringence thing.
Okay,
So yeah.
So
But I know that it has this problem.
even at 3 level, can't you have a bunch of derivatives there?
Yeah. But
You can, right? Or not?
But that would not give you nice equations of
Something that
motion.
is not set to 0 by equation.
Yeah.
It looks hard, right? Because either it's del squared or it's del mu f mu. Both are 0 by
Yeah, you can have df squared, whole square, df whole
df
squared, but it won't be local, at least in the way that you normally would like things to be local, and that your propagators look like 1 over p squared. So if that's something we want, then you can't have.
Okay.
Yeah. other things.
Yeah.
I think this is also related to whether you have ghosts, but not
And
ghosts.
extra propagating.
Yeah, an extra propagating.
So, yeah, maybe, as you say, maybe you can have
Yeah.
an element. It's fine. So those breadcrumbs were written assuming that there are no extra propagators. Is that right?
Yeah,
Now,
exactly.
thank you.
Yeah, it's very much still a theory of a massless vector in 4 dimensions, which has 2 propagating modes and can be described. Just now, the interactions that those modes satisfy is slightly different.
Thank you.
Okay, so there are fun. Let's start with what is EM duality and why this is a good thing to study on shell. So, the easiest answer is that EM duality is an on-shell symmetry. So there is actually there is one version that is off-shell, but you have to explicitly break log symmetry to write it down. So, okay, yeah, you
So
can.
isn't it just to make sure, because every time I have studied it, you don't have a Lorentz invariant S duality invariant field,
Okay, but
as
so-
far as I know. Or am I wrong?
So, it's the normal way in which you study SU, right, is you have some Young's theory and it has some charge states, and then you're doing some like a rotation between the charge states in that theory. Here, what you're doing is you've sort of taken the Young. So, if in that case you take the Young's coupling to zero, then you're going to get something that looks like a free maximum that has a continuous SO2. Right? I mean, so that is kind of the SO2 symmetry we'll see over here, except we're no longer just Maxwell. We have the square root.
I meant actually even without charged matter,
Yeah.
if you try to write down the Lagrangian,
Yeah.
at least, which has both S duality and Lorentz invariance, you can't do that, right? Because you have to take F to F dual and so on. And you can have one or the other.
Yeah.
I thought Ashok had
That's
these.
kind of
Okay.
yeah, that is kind of it. That is what I'm saying. That
Okay.
you can't write down
Yeah.
something that has both. So if you want to write down an action that has this FF dual symmetric, you have to break curves.
Sorry, what about the action epsilon mu alpha beta, del mu, del mu f alpha beta? Sorry, one minute. Put the Lagrange multiplier.
So
Put
F
the
tilde,
Lagrange.
F tilde.
Put the Lagrange A with df. Put the Lagrange multiplier, which is A and df plus A mu, d nu, f alpha beta. Alpha beta, put an epsilon with all of these, and f alpha beta, plus f alpha beta, plus 1 by g squared, f alpha beta, ff. Yes. Why isn't this nice? And this is the usual thing, right?
What is the so this is linear in F?
Linear. So this is A dual. That
Oh,
A is
this
tilde.
is not gauge and variant in the
Abelian.
this is not gauge and variant in the
It's not gauge. It is effectively, because now if I transform A by a derivative, because the epsilon it kills it. But make that A tilde if you don't mind.
Yeah, sure. I was saying, do it the equation of motion and the Bianchi, right?
Yes, you integrate out A tilde, you get the Bianchi identity for F. So that tells you that F is D something.
yeah.
And then that. Or if you integrate out F, you get F tilde squared. But with the G squared also. This is the usual way we
Yeah, I
establish.
mean, you're basically saying that, so this is the equation of motion, given the G tilde is defined like this. This is the Bianchi identity, why don't you add the Bianchi identity into the
As an equation of motion? Yeah.
with some.
This is the way people normally establish. Write down the Lagrangians for X duality. So I was just wondering why this was not a Lorentz invariant explicitly duality.
The equations of motion are S dual. Yeah. Does this have S duality in it? I don't know.
Meaning, sorry, I mean, you can look at it either in the electric frame, integrating out F, you get
So when you-
magnetic frame, integrate out
So here, though, you have in mind that G is going to 1 over G or something.
it will go to 1 over G because
Right. Whereas here, you're thinking of it vertically. So I don't know, I mean, you're doing scattering. I mean, so you're really thinking of this as some 3-level process. I'm going to make G small. I'm going to do this order by order in some coupling. And I don't know how to think of it as
So are we talking about abelian or non-abelian?
Abel.
yeah, Born and Feld was
Born and Feld is fully Abel.
Is
Abel.
is abelian?
Yes.
Okay, well, maybe I'm
Yeah.
when I try to
So-
okay. So okay, we never do it. Okay, I maybe understand correctly.
No, I'm probably understanding the goal wrong. This has both the electric and magnetic field strengths in it,
Yeah.
and it's completely fine, right?
Yeah, that's okay.
F wedge F plus F star F wedge F star F, right?
Yeah, I think, I mean, yeah, this is FF.
Yeah.
One of the gauge fields is different. A tilde is not. Yeah.
This is like a Lagrange one.
Lagrange multiply, but it becomes a gauge field, a
Yeah.
dynamical degree if you integrate out of.
Right.
Fine.
I will not say anything more about this. I will just say
Sorry.
no. I will just say that we are anyway going to study it on shell, and we're going to study it quantitatively. So the way that to have an action that does this when G goes to 1 over G is not that helpful because we are very, very solidly in perturbation theory, and we don't have any access to anything that's 1 over G looking. The other thing I would say is, again, that we're going to be on shell. So I really do want to think of this as,
But Shiraz, is a way of doing this for ball and field also?
I would imagine. I'm not sure. I would have to think. But I would try first by just replacing FF by bond and fell.
Okay. With the same thing.
With the same thing. And then you get what you get. Right? You on integrating out the F's. Maybe because it's not quadratic, you have more issues. But I don't really know.
Yeah, that's really what I was worried about. It's an interacting. This is some Gaussian integral.
No.
okay, so I don't remember the paper that does this now off the top. I should have added the citation in here, but they tried to do it for bond and fell.
Okay, so maybe I think it's
So maybe
because it's
that's
not
not-
Gaussian,
yeah.
makes it more
Yeah.
difficult for me.
I don't want to say anything about, I don't want to say or like a different vector field theory, but I think you can't do it
But the point
specifically
is
for
that
this
that
one
action does
example.
have this electric magnetic
It
development.
does,
Then you want to kind of exploit.
yeah, it does. And sorry, so what I mean by electromagnetic duality is this rotation. In
Sorry,
this
can you
case.
elaborate that?
So, okay, so this, your G tilde is this, what would go in normally to your Euler-Lagrange equation of motion.
Okay.
So the equation of motion is just derivative of G is 0. And this is the Bianchi identity. And then if I look at rotation, so if I take like F to cos theta F plus sin theta G, then this is infinite. As long as this condition is satisfied, which it is for bond and fell. Yeah. So this condition was given by Tiaras. But yeah, I don't know the answer to your questions about the Lagrange.
Okay.
So okay, so this is on shell, but on shell in the sense of equations of motion. I want
Is that
yeah.
easy to see that that's the equation and that's the condition?
Um, I don't know. I don't know off the top of my head if that's easy to say.
So the statement is that this equations of motions are invariant under some rotation in the FG space if that condition is met.
You have to be careful because G is sort of determined as a function.
Yeah.
So when you take F to
Yeah.
then this will also change, and then you have to put that in there.
So it's non-trivial that it's
It's not, I mean, it's definitely true that this is invariant as long as this is true. It's not,
Yeah.
so I don't have a argument off the top of my head because, yeah, I can't see exactly how. So now F will have to go to this new S prime, and then G tilde will be G tilde of F prime, and then you have to see whether this equation is.
At the classical level, this is exactly this with FF replaced by
right.
L of F.
Yeah. Right.
But that equal to 0 means no.
That
No,
equals,
then it would be FF tilde plus,
Sorry, I don't understand.
um,
Well, sorry, what did you say? Shiraz?
and so the first line, ignore the second line, that is what you would get from this if you replaced FF by L of F.
Yes. 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 Okay, you can go ahead.
okay. So in case you can't tell, I really think about scattering amplitudes. I don't love Lagrangians very much, but for scattering amplitudes, this condition, if this condition is satisfied and you're looking at the scattering amplitudes, then in 4 dimensions, all this tells you actually is that the number of positive and negative velocities have to be equal for an amplitude to be non-zero. Okay, so this is just a statement of helicity conservation.
Tilde was star, was dual, then you F tilde.
This is tilde. Oh, this tilde you mean? Yeah, this is epsilon.
F tilde, scatter. Yeah.
Yeah,
So
that's
that
the usual.
that equation was just D everything you say, no? Then yeah, fine.
Yeah, exactly. Yeah. Yeah. So in maximum theory, this would just be df equals 0 and then df tilde equals 0. Yeah. This is the usual equation of motion. Yeah. So for scattering amplitudes, all this is telling you is that n plus has to equal n minus. Okay, so when I say this, it's important for me to clarify that all of these are outgoing states. So you can use crossing symmetry and change things around as much as you want. But yeah, once you in the convention that everything is outgoing, you have to have an equal number of positive and negative states. Yeah.
Is theta the possible?
Yeah, it's the epsilon cathode. Yeah. Yes. Yeah, which is why this is the PMP identity, and then that would have been P as the equation. But really, this is how I want to think about electromagnetic duality in Born-Feld, which is just that amplitudes that violate the symmetry must vanish. So it's a sort of a sweeping statement. So I want to just show you what the Feynman rule is for
The
Born-Feld.
last statement, what was it? Amplitudes and
That the number of positive and negative helicity particles have to be equal for Born-Feld to give you a non-zero amplitude.
I see. And how did that follow from what you said before?
It doesn't yet.
Okay.
Yeah. So it's a property of Born-Feld.
Okay.
Yeah. Give me 2 slides.
Sure. So it's just a separate condition.
It's related.
It's related. Okay. Wait. Yeah.
Yeah.
Right.
Yeah. So okay, I just quickly want to just point out that again the same thing, just like Park-Taylor. If you try and put Feynman rules together, this is just the Feynman rule at 4 point. This is the amplitude at 4 point, and then you have this is like it is a high derivative theory, so you have at every endpoint a new rule, which is not true in calculus. So doing this calculation with traditional methods is just a very bad idea. Okay, so non-traditional methods exist, and okay, so these are just for now just names of methods and people who have thought about the methods. But the main thing here is that you can calculate every endpoint amplitude using these. So it's not like it gives you all the tree-level Born-Feld amplitude. And we use these methods that are recursive. Okay. Well, this one isn't recursive, but it's still nice. So to sort of answer Shiraz's question, in all of these methods, in most of these methods, this symmetry sort of emerges. So you find that these amplitudes have to be equal. These amplitudes have to vanish unless the helicities are equal. And given that there are no other assumptions you put in, the only source of this symmetry can be the fact that the equations of motion behave in this FG rotation. So, okay, there is, if that's not satisfactory, you can rewrite your Lagrangian in terms of F plus and F minus, where the F plus gives you the positive helicities, F minus gives you negative helicities. Redo this Gauss-Zumino condition and you'll find that it's the same.
So could I understand what it means for the Lagrangian to be electromagnetic? So does that mean that when you compute scattering amplitudes of the photons,
yeah,
you get the same answer as the scattering amplitude when you compute of the dual photons, provided you replace G by 1 by G?
Yes. Yeah, that's one way of thinking about it. That's, for me, I will mean more about, I will think more specifically in 4 dimensions.
Yes, question.
And so I will have this, I can think of it as F plus and F minus.
You're saying the two.
In the spinor representation of F, instead of using a vector, instead of using F mu nu, I can use the spinor way of writing it. So there's F plus, which is just the positive helicity, and F minus just the negative helicity.
And the electromagnetic duality exchanges the two?
Yeah.
But there's no G goes to 1 by G?
No.
I see.
So I think electric magnetic duality for you is just that Zumino condition, right?
Yeah, it's just the Zumino condition, which on shell is this.
Yeah.
From the G goes to 1 by, from the G goes to 1 over G, I don't know how to think about it because,
So you have a different notion of electron. I mean, normally you think of G goes to 1 over G.
Yeah, I don't know actually what the relation is between those two. As I said, when you take G to 0 in the usual case, you get this continuous symmetry, but that's just for the Maxwell once you've had billion times data. And so this is kind of saying that, I don't know what the analog is.
Okay, so for you, all that it means is you interchange positive and negative, and that implies positive and negative helicity.
Yeah.
I see.
It's I'm thinking very just in terms of perturbation theory and in terms of on-shell.
But I'm just wondering why the word electromagnetic duality is the right name for it.
Well, because it exchanges F and F. That's kind of the, We should maybe have used a better name, but this was already being used in the literature, so there's some
Fine. But
Potential
you're not implying
value.
that it's SD validate.
No.
Okay, fine. Now it. Thank you.
It's something more general, right? Because it's not just exchanging F and F tilde. It's more like you have F and F tilde and you can do any rotation you want. And the usual one is just 90-degree rotation.
Yeah, yeah.
Like
What F tilde is F and G, right?
F and G
yeah, but like G becomes F tilde and actually.
in Maxwell.
Yeah.
Maxwell. So you can do that, but on shell you have exactly two states, so this statement is you can flip those two states.
One shell is only 90
Plus and
degrees.
that's minus, and so
And this condition is powerful enough to narrow the amplitude down to precisely one-third amplitude.
And that's what I want to ask.
no. So there are other Lagrangians you can write down. Or there are other scattering amplitudes you can write down.
So there,
Yeah.
I see.
But
So
they will
these
not
numbers
be-
that you mentioned somehow.
Yeah,
Take care of
exactly.
those
This is why in neither of these cases you're actually, so here it's assumed, so you use it, but that's not the only thing you use to construct. And in the other two cases you don't even use it at all, it just emerges. So it's not like that is what. Yeah, you use the fact that-
Condition or what?
No, you don't use anything related to inequality, you just use the fact that this is some brain theory, and so you have a full multiplet, right? You have phi, which is this Dirac-Born-Infeld scalar, which is telling you where is this, the brain. You have some fermions, so you have two fermions, let's say, if you're in n equals 2. And then you have the vector. And just the vector, if you just look at the vector path, that's Born-Infeld. So this one over here is a Goldstone mode in the space-time symmetry theory. And so you can use that fact to fix all of these amplitudes, all of these amplitudes. So that is what disbursement is. The second one we'll talk about more tomorrow. That's
Should we ask a very stupid question? Please forgive me. Doesn't parity interchange positive and negative elicitly? So then, is it right that any theory that is parity invariant has this plus minus split?
Does it say that you relate the amplitude?
It says you relate, yeah.
Rather than that it has to be equal?
So it will say something like in Yang-Mills, for example, which you would, I mean, if you took that seriously, you would say that violates parity. It's not true.
Oh.
Yang-Mills has amplitudes with unequal helicity gluons. But all you're saying is that a plus, whatever, an amplitude with all pluses, let's say, will be related with the correct phase shift to an amplitude with all minuses. That's parity.
That's parity, yes. And what is the statement here? That
The statement here is that you just wouldn't have an amplitude with all pluses because it would violate helicity conservation.
okay, so you would have amplitudes only with the number of pluses that is equal to the number of minuses. Okay, fine.
That's it.
different.
And everything else will go to zero.
Thank you.
Can I ask one remedial question? Sorry. I mean, it's a mathematically well posed problem to try and start with the Born-Infeld and so on. But I mean, just if I'm doing S matrices in asymptotically flat space, is there a physical situation where you want to keep the higher derivative contributions in the Born-Infeld and neglect the acceleration terms? I mean, the reason I'm asking is usually I think of the Born-Infeld, for example, as being a good way if you had some big magnetic field or electric field which is big in intensity but slowly varying.
Yeah.
I'm not, just for S matrices, is there some situation?
I think so, but I based this on just the following fact, which is that if you're looking again at it as like the full supersymmetric Born-Infeld theory, you can do that for the scalar, where you can take, there's some double scaling limit you can do of the sub-leading piece and the leading piece, so that you can just make the leading piece drop, and you only get the sub-leading piece. That's called the Galilean theory.
Okay.
So you can do this for the scalar, which makes me think you can do something similar for the vector. But the vector is, so that theory you can fix on shell, but I don't think you can fix the corresponding vector theory on shell. It doesn't have nice enough properties. Scalar. But I think it's possible.
Yeah, I was thinking again about this EM duality thing. And I think there's a simple understanding in terms of the Topology model. So you have a space of, in Maxwell, you have a space of F and F. Tell me if I'm right. And then you're talking about rotations.
Yeah.
That's what, right?
Yeah.
But then the usual G2 duality is the reflection, which takes F to F tilde and F tilde to F. Whereas your symmetry can only take F to F tilde and F tilde to minus F, which is very different from taking F tilde to plus.
Maybe that's, I mean, because you're right that it's definitely, one difference between them is that one of them is discrete and the other one is continuous.
Yeah.
So, yeah, it's not a reflection. It's the fact that you can do the full rotation.
So
And
this is a completely different thing with the usual EM duality.
in my opinion, yes.
Okay.
But I don't have a very concrete way of stating that.
Which also connects with the fact that you don't do G equals to 1 by G.
Exactly, that's
continuous.
Yeah.
Yeah, and so actually, I think I didn't answer your question before properly. So the fact that you can do this plus or minus on shell, you can also do plus going to a combination of plus and minus,
Yeah.
and it'll still work out.
Yeah.
Yeah.
In this double copy method, what is assumed about the theory?
That will be whole of t or thereafter. So yeah, but what is assumed is that certain linear relations called BCJ relations are satisfied by not by actually nothing is assumed about Born effect in that case, other than the fact that it is the double copy of two things.
The double copy
Of two theories, Yang-Mills and sigma model theory. But
No,
yeah,
no, this is the sentence that
okay.
Yeah.
Yeah, so that is how you define it in that case. Yeah. But these are all things that agree at leading order is very clear very unclear once you try to do the correction, what you mean by the theory. In the EFT sense, what are you using to fix those terms?
But about Sandeep's question, in string theory on a brain, this would be the leading low energy effective action.
Yeah.
Right? Because if, for instance, you could have had two F to the 4s with different coefficients. But in string theory, it actually comes with this
Yeah, this specific square root action.
Right. So the 4 do on amplitude, the corrections to this will be suppressed by two derivatives down.
Yeah.
Because that would be del squared. So in string theory, for any given amplitude, this would capture the leading low energy effective.
Oh, I see. The leading tree level.
The leading low energy, lowest order derivatives.
But so you can do the same thing for the scalars as well in the supermultiplier, but there is a scaling limit where you can get rid of the leading piece and get just the subleading piece, which is what I was saying. Like it's possible that you can do that for the vectors as well, but I don't think it's.
Yeah, I think Sandeep just wanted one context where it was.
I see.
Where it would be useful to know this capture.
Yeah.
I see.
Then
So you're saying just take the plane.
Yeah, it's literally the leading one.
Yeah.
Okay, thank you.
And dimensional analysis didn't guarantee that because you could have had two F to the 4s.
Yeah.
But in string theory, we know this is the right one
That's the one that's selected.
because of your 1.6 these also.
Thank you.
Okay. So we kind of already talked about a few of these things. So Born-Enfeld itself is this action over here, right? That's the square root action I showed you right at the beginning. That's probably an hour. No, I'm kidding. No, the questions are great.
There's a stick there, Shruti, if you want to intimidate us.
Hey. No, I already showed you the Born-Enfeld Feynman rule, so if that didn't intimidate you, I don't know. But okay, so yeah, so if you're looking at a D3 brain in 4D, so it's space filling, then the low energy effective action is Born-Enfeld and given by this Lagrange. Now, if you compactify on a circle and you basically de-dualize and you go to now this three-dimensional configuration over here, right? So now you have a modulus as well, right? Where this x is a scalar that is given is basically what happened to the polarization that was along the compactified. So this is all to say that when you go from 4 dimensions, 3 dimensions, then the action looks like this, where now you have this the extra polarization mode has gone into this x scalar. Okay. Now, because you are in 3 dimensions, a vector is not really a vector. You can use a Legendre transform to rewrite f as some other scalar, which we call y. In terms of what is happening in the brain picture, it's basically telling you that D2 and 4D is empty with 5. So you've traded in your A mu for 2 scalars, 2 scalar moduli, and because there are now 2 transverse directions, you can rotate amongst. That's also very clear from just the action over here that I can rotate between x and y.
Wait, but one of them is periodic.
One of them, well, I have taken
Some limit.
yeah.
Okay.
Yeah. Good. So this is in Kroszinski's text.
So you've taken the limit where the M theory circle is not infinite.
Yeah, exactly. So, yeah, exactly. So I'm left with these 2 scalars, and these 2 scalars now are truly in these transverse directions, and I can rotate between them. And because I can rotate between them, I have this U1 symmetry that I can use when I'm thinking about amplitudes, right? So in the amplitude sense, I have some vector amplitude in 4 dimensions. If I reduce it to 3 dimensions, I'll end up with a scalar amplitude. That scalar amplitude has to have a U1 symmetry. So it's easy to see that the fact that these vector amplitudes, they started off as having to have equal number of positive and negative hemispheres. Right? So you needed n plus equals n minus. Now, it's very easy to see how that means that there needs to be a U1 symmetry. Okay, so that's this direction of implication. All I'm doing is I'm going to restrict my external momentum to 3 dimensions. I define my scalars x and y appropriately. And then I say that, okay, I have equal numbers of z's and z bars in my amplitude.
And the limit in which you get this decompactification is a strong coupling limit.
Is those?
It's the very low energy limit or very strong coupling limit. Right? I mean, basically the brain coupling is G.
Yeah.
G string.
Yeah.
And you want the M theory circle to go to infinity, so G string goes
So
to infinity.
you've compactified on a circle and you're taking that circle's
You compactified in string. Okay, first. So
the first step.
first step is compactified string theory on a circle. Okay, good.
You've compactified, along the word volume on a circle.
Yes.
Yeah. And then that is
That circle size you take to 0, original circle size you take to 0, so this becomes non-compact.
Exactly.
That's fine. I was talking about the second step.
So the second step is, it depends on how you want to read it. I usually think of it in this sense, which is literally that any vector in 3 dimensions is just dual to a scalar.
But a periodic scale.
A periodic scalar, but you can, that does not affect the scattering, right?
Oh, it does not affect the scale. I see.
So all I'm saying is that here I end up with a theory that generally I can rotate between these in terms of the scattering amplitude. So I can actually just, this is just true.
I
That
see. You're
the
saying the
number
fact
of
that it's
z's
periodic
is
is non-conservative.
Hmm.
That's, I see.
So this
in perturbation
is-
theory, you
Exactly, yeah. At leading order perturbation
I see,
theory, this
I
is
see.
all still true.
I see.
It still works. And again, as I said, this is the sort of the easier direction, which is that given that my vectors have this property that I have to end up with a U1 scalar. U1 or S, yeah, you can call it whatever you want. Basically, you can rotate between X and Y.
I see. Thank you. Perhaps another way of saying it is that the place where periodicity makes a really big difference is when you're on a compact manifold. Like I'm just an R2 target. Okay, I agree. Thank you.
But non-perturbatively, then you will have 2 compact scalars. And then the symmetry will be that of torus. I mean, if this go to the SL to Z. And then that transformation will also change the coupling, right? Because one of them is the coupling.
Yeah. It's just because on non-perturbativity you have M theory on it.
Yeah.
So
Yeah, versus
certainly.
yeah.
No, but I'm saying that G should go to one of those sheets.
Yeah. So that will be the SU value technique.
Yeah. Well, it's tangential.
Yeah.
Okay, I don't quite see what you said, but I will take your word for it. Okay, anyway, so for us, this is enough. I mean, that this condition is true. That on shell for scattering amplitudes, you see the fact that you can rotate between x and y and you get this u1 symmetry.
This is already interesting. It hadn't entered my head that the periodicity doesn't matter in potential.
Yeah,
Very
but really, okay, what we want to do is go in the opposite direction, right? You want to be able to say, why does this theory have EM duality? It has it because it's related to the U1 of this lower dimensional theory, and the U1, so rather than the saying that, okay, this EM duality reduces to U1, you want to say the U1 oxidizes to the four-dimensional symmetry. Yeah, so I want to go in the opposite direction. That if there is this symmetry in 3 dimensions, there has to be this other symmetry in 4 dimensions. So I want to say that if a duality violating amplitude vanishes in 3 dimensions, then the duality violating amplitude has to also vanish in 4 dimensions. So at 4 point, this is very easy to see. You just write down the only thing I can write down, which is permutation symmetric and has the correct little group structure, it has the correct mass dimension at 4 point. There's only one thing it can be, and so I put a general coupling constant sitting on it front. And then I say, okay, I just set my momentum to 3 dimensions. That gives me this. S squared plus t squared plus u squared is generally not 0, which means for this to be 0 in 3 dimensions, alpha plus minus has to be 0. Okay, so all this to say that generally it seems to work.
Quite understand.
Okay, so so this is the thing that I want to show.
But what is your assumption symmetry?
So I just want to write down the most general possible
Of scalar fields. Of scalar fields.
of vector fields in 4 dimensions.
No, but I thought you start from 3D, then try to say something.
I want to, so I want to say that if I started with a 4-dimensional vector theory, that vanishes in 3 dimensions. Then the vectors have to vanish, the vector amplitude has to vanish in 4 dimensions. Right? So I start with this full vector, this is just a regular 4-dimensional vector amplitude. And I'm imposing that it vanishes in 3 dimensions.
Basically, the point was that it was not multiplying something that was 0.
So it did. Yeah. So you want to impose the condition that it vanishes in 3D. It doesn't vanish naively, which means that the coefficient has to be 0. Yeah. But if the coefficient is 0, then it's 0 even in 4 dimensions, and so this has to be 0. Is the
So this says that roughly as many amplitudes in 3 dimensions as in 4 dimensions.
for this particular mass dimension, for this symmetries, which is fully Bose symmetric, for this helicity combination,
It's very
at 4 points.
At higher points, it will not be true, right?
It will be
It
true.
will.
So that's good that it will be true. But we'll see how. So
Sorry,
yeah.
3 dimension, you just have theory of two scalars which is sort of symmetric.
Yeah.
That's the only constraint.
Yeah. So if I started with something that violates the duality, I'll end up with something that violates the U1 of the 3-dimensional theory.
The rotation.
The rotation. The
No,
3.
because that came from there only, right?
Well, no, that was just to say that this implication works.
Yeah.
But this is the sort of easier direction of the implication. I want to go in the opposite direction. I want to say that I know that this is true.
You want to
So
prove the four
can I
dimensions.
use it to show that this is why EM duality exists? Because otherwise it's kind of mysterious why this should be what is picked up. Yeah. So you want to say, given that this is true, this is true. Yeah. And this is just a easy 4-point thing, which is like, okay, if I just do this at 4 point, does it work? Says okay, it works.
And is det F the only thing that would lead to something 3-dimensional rotationally invariant?
Presumably, I mean,
So any function of det F would have.
presumably, yeah,
Yes.
but that's not the right order for this.
But that's not the right.
That's det.
Why did you say this? Because Born-Infeld depends on det F. And she.
I don't know if that's true. I think it also has to be specifically the square root action.
Well, you had square. Why understand? So,
I mean, so,
Oh,
so,
I
so
see.
you're relating
I
the coefficients at every order as well,
uh-huh.
right?
Uh-huh.
It's not an arbitrary function.
Yeah, that of something. That of something. One plus
It's not an arbitrary function.
function. That as Vijay said, that of 1 plus f.
Yeah.
But if I make it a function of that of 1 plus f, that would also work, right? The square root presumably gave the square root in your final answer with the. If you could go back one slide.
Yeah.
Yeah, then the square root was visible.
So okay,
No, but all that duality, etc.
No, just algebraically.
algebraically, I see what you mean. That it should just still have that U answer.
So you want symmetry.
Yeah.
And therefore.
Okay. So I'll point out
Is the
what.
first step, then you can just equalize.
No, so he's just saying at the level of the action, you can rewrite this as this.
Sorry, just to ask you a remedial question. From second to third step, there is in effect a S duality between the 2 plus 1 dimensional gauge field and a scalar. And just to ask you for a general form of action, would it always give you back this object? I don't know that. I mean, you trade f mu for a scalar x.
You don't trade all of f for a scalar. You only trade the part that's along the circle.
You trade.
I mean, this still exists. There is still some polarization along the direction of the d2.
Along the d2.
But there is one part of the d2 that no longer exists. There's one polarization that was the 3, and then that becomes the same.
No, but when you go from line 2 to 3, you get rid of your gauge field completely.
Yeah.
That's what I'm saying.
Yeah.
And that's where you then see the full
Yeah.
rotation and symmetry,
Yeah, that's
right? And it just can't do it in my head or whatever, but if you had something else,
I understand the question.
would it be true?
Yeah. Something saying you're just replacing f mu nu by epsilon mu nu alpha del alpha chi.
Yeah.
And is that always valid? Does that come from this kind of manipulation?
I would think so because definitely if you're
It would
looking at
always give you back the same.
If you replace it, it will be good.
If you replace it will.
But is that always allowed?
Yeah.
Also, the first step, how does we carry out the first step?
But the first, that is just the dual.
sorry, so this step is the more trivial one. I'm putting it up to this is the non-trivial one for an action that doesn't have the square root, etc. This you can always do, you're just rewriting what you mean by certain modes in your action. Right? You're just saying there is only one option.
But it's an off-shell statement, right? To see the symmetry. You should get back this, maybe it's obvious, you should get back the same form, right? I mean, in the second
I see
line,
what
the
you're
gauge
saying.
field and the scalar look different.
Yeah.
In the third line, they look the same.
So I
right?
think that the fact that there is a U1 probably depends on exactly what this is. But the fact that you can rewrite it as a scalar is a trivial.
No, that of course is but okay. I
Yeah,
mean,
the U1 part
is
is-
there a dependence on the Born-Infeld specific type to go from?
Yes, first and second is just dimension reduction.
I think so. If you added other stuff over here, it wouldn't have the same. It wouldn't satisfy you.
So that's
Yeah.
that's tied to the if you
I mean,
want
the easiest example is that if you add high derivative corrections, you no longer have this.
No, but I think Shiraz's point was take a general function of depth,
Yeah.
Yeah.
1 plus n.
So that I'm not sure what is.
And then
but
root it.
definitely,
That is the question.
Yeah.
but definitely, if you add it's not true in general.
Okay.
Yeah.
Great.
But I
This
don't know
is easy
about
to
that.
figure out.
Yeah.
Please go on.
Okay. So what we are going to do again is that you have a dual. You start with the duality validating amplitude in 4 dimensions. You impose that it vanishes when you reduce it in dimensions, and then you want to say it also vanishes in 4 dimensions. There is no other option. Okay. So to do this, we'll set up a sort of recursive argument. So this is very similar if you're familiar with BCFW to the BCFWR.
So, and now what are you trying to show again, please?
This
For higher
this
forward
bit.
functions.
Yeah.
4 is done.
4,
4 point, we saw it.
this is sort of the seed of our recursion,
Okay.
that it works at 4 points,
Yes.
and then we're going to say at n point it's going to depend on n minus 2 point.
Yes.
And so if it works for 4, it works for n.
Fine.
Okay. So to do that, we'll set up these recursion relations. And the way that we're going to do that is we're going to introduce this parameter z. The way that we introduce Z is so that when Z equals 0, you get the unshifted actual physical momentum. So AN, the amplitude evaluated at 0, is the amplitude. That's where it is. At Z equals 1, this vanishes, so what you get is Q. So what is Q? Q needs to satisfy the following. So you want that this is a good on-shell momentum at every point C. Right? So you want to say that pi dot qi and qi square are 0, so that pi hat whole square is 0. You also want momentum conservation to be satisfied everywhere, so this needs to be true. Okay. Now you still have some freedom in choosing q, and what we want to do is choose it so that when z equals 1, then all your momenta lie in a 3D subspace. This is because we know what happens to the amplitude when you are in a 3D subspace. You know that it vanishes. Right? So you choose this, and so this is how you're going to choose Q. And as I said, it's because now you know at two special points what's happening to the amplitude. At z equals 0, it's the unshifted physical amplitude. At z equals 1, it's 0.
So can you explain why it lying in a series of different laminas?
Oh, because we're assuming this condition. For a duality violating amplitude.
Nice.
Yeah.
And n is any vector?
N is anybody. Okay, yeah, you can choose. Yeah, I think you're not allowed to choose it.
Oh.
Yeah, but I think you're not allowed to also choose it to be one of these. I think some problem happens.
I think, you will choose it independent of the moment.
Yeah.
Okay.
Yeah, we leave it fully like undetermined.
But you will require time like space time. You require space time.
Yeah.
So the previous proof is essentially also that the 4-point scattering can always be brought into three space dimension and three dimensions.
I get that is one way of saying it, though you lose some information when you come to it. So you always lose information about helicity when you reduce to 3 dimensions. So it's that's why it's non-trivial to say that if it vanishes in 3 dimensions, it vanishes in 4 dimensions. But that's what we're trying to do.
Because the number of parameters of the amplitude, final amplitude is the same.
Yeah.
It's the same, right? And isn't it that some of the coefficients in 3D don't vanish when you...
Yeah, so if the number of parameters was the same, then generically that would happen. So I feel that that's what you're arguing.
Okay, so the unshifted amplitude, as I said, is the first special point, which is z equals 0. So you know what it is. This is just a regular contour integral. Contour is around 0, right? But we can do something else. We can also add this.
So I missed your contour integral, if you don't mind.
This is the one we're looking at.
Okay.
So it doesn't matter. Yeah, because we want this additional 1 minus z in the denominator. This doesn't introduce a pole because at z equals 1, amplitude vanishes. So for a duality violating. So now you know that the 4-dimensional duality violating amplitude is given by this contour integral. Again, everything's at 3 levels, so you know exactly where the poles are. The poles are just intermediate momenta going on shell.
And you want to show that the left-hand side is 0.
You want to, yeah, that's it.
That's what you're doing.
Right. So to do that, so this is the non-trivial bit, which is to show that at z equals infinity, there is no residue, right? Because what I ultimately want to do is take this contour, blow it up, use Cauchy's theorem, and then just pick up the residues on the poles that are local poles, so that you just factorize into lower point amplitudes of those poles.
And you did the z over 1 minus z, so as to give you good behavior at infinity.
Exactly. So so the Born-Einfeld amplitude itself behaves as 1 at z equals infinity. You need this to behave as 1 over z squared. So just having 1 over z is not enough. You need that extra 1 minus z so that you get 1 over z squared. So
That's where you use the pole at one, you control it using.
yeah,
You know that it vanishes.
it vanishes. Yeah. So it's not a pole actually. Yeah. So good. So when you do this, you pick up the residues at these red poles, and what you're interested in is the residue at the pink pole. So you get this, where what I've said is that on these intermediate momenta, you need to look like some L times R, so lower point left and right amplitudes. just to parse the formula a little bit, this pi square of z is when the intermediate momentum goes on shell. But yeah, I mean it's pi square, so it's quadratic in z. So actually there are two solutions with pi square being 0, which is what I call zi plus minus. But it doesn't matter. Actually, the only thing that matters is that an depends on lower points. Right? Additionally, if n plus doesn't equal n minus, then you can't have so then nl plus nr. I'm not reading this out, but this does not equal this, right? So that means that at least one of these amplitudes has to vary.
Yes.
So that means that if you don't have a lower point duality violating amplitude, you can't have a higher one. Yeah. So by induction, you're saying that start with my seed as 4 point, which we saw, this works. So then you're just saying that all end point is 4.
So the really important thing was that there was no contribution from infinity.
Yeah.
The rest was sort of guaranteed by structure.
Yeah, and that comes from the fact that you know that that there is a particular behavior that bounds.
So then what you show is that the Born and Feld S matrix is fixed by this asymptotic condition and the U1 symmetric condition.
Yeah, actually that.
Asymptotic condition is specific to the Born and Feld action. I mean, do you use that fact? Like, it went in there, if you had acceleration terms in one, it wouldn't be
Yeah.
generated.
It wouldn't be generated. Repeat the argument. Yeah. So, okay. So the way that we implement this is that
That's still
basically, if you have a spinor helicity, right? So if you're looking at everything in these variables, then you know that every external positive helicity particle comes with a square, and every external negative comes with an angle. Okay. So the way we do this shift is that if you have a negative helicity particle, you shift the square so that you don't get this extra, the extra stuff that you're sort of guaranteed to have just because it is an external positive helicity or negative helicity particle. So for example, over here, I would, since they're all pluses, I would shift the angle. And so there would be no contribution z, and then this would scale as z equals the z to the z.
So this was these such questions why it scales as z.
Yes.
Yeah, I had the same question. Okay,
Yeah.
but
So first thing to know is that that's how we do the shift. That we're trying to reduce the scaling, and so you want to not include the external wave functions. Okay. Yeah, so the external wave functions, actually what I mean is some kind of polarization tensor, but a polarization tensor for F, not for A. Yeah. So, okay, so that is true, and now the rest is so the amplitude has to scale as, so the amplitude has mass dimension 4 minus n. Right, then you have this is the mass dimension of the coupling constant. Okay, so this is actually n minus 2. This is minus 4. This is 2. Minus 2. Plus 2n minus 4 is what you get. That's the mass dimension of the coupling constant. So then this gives you n. Yes. Okay. So this gives you n, and then you subtract out the fact that you don't have any contribution from any wave functions, which gives you another minus n over here.
could I say it this way that your interaction term in the Lagrangian was f to the n?
Yeah.
And you're doing a subtraction for f to the n.
Yeah.
And therefore you get 0.
Yeah. So this is, yeah, okay, maybe that's a better way of saying it. But basically you're counting the mass dimension of various things, and you know that when you do this all line shift, basically what you're saying is how many momentum factors do I have that don't belong to an epsilon, that doesn't belong to a polarization.
Yeah. Just gauge in various forces some growth.
Exactly.
Remove that,
Yeah.
and then the rest is
Exactly. Yeah. And you can do the identical argument for gammas. Except now this will be 0, right? Because you don't have any coupling constant mass dimension. Yes, we do the same thing. It will give you 4 minus 2n, and that is the scaling of an online shift. So,
And this also answers, I think, Sandeep's question, because now if you had 2 extra derivatives,
yeah.
apart from the f to the n, it would grow like
Plus.
s squared plus 2.
Yeah, plus actually any number of derivatives.
Right. Let's say I had 2 extra derivatives that would grow like s squared.
Yeah.
So then it just would not work.
Yeah, so for any extra derivative I add, I have to do a subtraction as well. So in particular, if you're dealing with Dirac-Born-Haskell theory, then it's like D4, phi 4, and I have to do a subtraction for each of the phi's.
So what this shows is not that the Born-Haskell is uniquely picked out by this condition, but rather any amplitude that preserves helicity is picked out.
Yeah, exactly. So all this is saying is that if you don't preserve helicity, you have to. Okay.
Sorry, Shruti, this is an aside,
Yeah.
but just let me ask it, then you can explain later to me. So we are focusing on the abelian case here,
Yeah.
but just as a statement, is it true that the non-abelian Young's theory has this helicity preservation
No,
property? It
no,
doesn't even.
no, it doesn't. Not at all. Not even close. Yeah, there are a lot of different hemispheres.
Thank you. So in particular, sometimes people evoke this, symmetrized trace prescription for generalizing the Born-Haskell to the non-abelian case.
Yeah.
And that has no analog story built up for that. I was just curious because often we do use that and it works. It's supposed to come out of string theory or something.
Is that right?
Well, that's what
I
people
don't-
claim. I never checked.
Yeah.
I
People
haven't-
claim that.
Yeah.
Yeah, I haven't seen the derivation of that action as the actual low energy limit of anything. But if you write it down, you can figure out what the scaling is. But I think what you don't get is the fact that it's in the same supermultiplet as some nice scalar. So basically, you have to have some non-abelian TBI scalar, and I think that, at least to me, it's very unclear what the properties of that scalar is. Yeah. So, wait, I'm about halfway through.
You're doing
Is
well.
that, is, I thought this would be the easy trick of the part.
8 years, you forgot it.
No, but okay, no. I'm glad that we're somewhat on the same page, which is that we can now have this sort of picture of why there is this symmetry in 4 dimensions, which is that there is this U1 symmetry in 3 dimensions and an opposite exists.
Up to 1 o'clock is okay. So up to 1 o'clock, it's fine.
Okay, wherever I reach till, then
Yes.
it's in the hands of the gods. Yeah, so okay. Fine. So now what we want to do is go beyond the leading order and go to loop level. Okay? And in particular at loop level, we're going to deal with the amplitudes that are what we call self-dual and next to self-dual. Again, these are just terminology that exists in literature, so we borrowed it. I don't particularly like it, but so this is the all plus and all but 1 plus amplitudes. And if you're familiar with supersymmetry, you should see these and immediately think, oh, okay, these are the ones that automatically vanish in any vector multiplet, which is true. And that's exactly what we've used. The fact that these vanish in a supersymmetric theory is going to help us calculate these amplitudes in a non-supersymmetric model.
And you'll remind us why in supersymmetry.
Yes. Oh,
Sorry.
no, but I can. I was not going to, but yeah, I'll do that.
I should know it, but
No, yeah, I'll do it in a second.
Sorry, beyond leading order means you include either loops or you include
Just one loop.
Okay.
Yeah, just one loop.
Shruti, I can ask you afterwards, so you can just go on. I mean,
Okay.
you know that. Yeah.
It's not actually, it's just the supersymmetry word identity
Uh-huh.
that guarantees that has to go away once you have a vector multiplet of any n equals 2, n equals 4. Yeah. But yeah, I can.
It's fine.
So, okay. So the first, sorry, these are the two things that we'll be using.
It comes from a d4 theta term.
It comes from so again, this is just a statement about amplitudes, right?
Right.
So I'm going to just say
Oh,
that,
you're not going to write down the Lagrange.
yeah,
Okay.
basically never. As far as I can get away with it. So there is gamma plus, psi plus, let's say A is whatever R index, and A over here, right? So the water energy says that Q acting on this needs to be 0, and Q annihilates all of these. Well, okay, Q or Q dagger, depending on how you're writing this. So the only term you get is this N. Gamma plus equals 0. N is generically non-zero, so that needs to be 0.
The first line is just that has been half compared to all the others. Or
This is just the water.
no, and oh, I
The
see.
supersymmetry water. So it's saying that when I take an amplitude and I apply Q on it, it needs to vanish. It's just an on-shell supersymmetry water identity. I can do the same thing again now when I have one of these being psi minus, or gamma minus. And then now I have two amplitudes. I have n minus 1, gamma plus, gamma minus, sorry, psi minus A, psi plus A, plus n gamma plus, gamma minus, gamma plus is 0. And you can check that this means that both of these have to be 0 for a generic external momentum formula.
Thank you.
Yeah. So in supersymmetry, both of these amplitudes have to vanish. It's two of gluons, vectors, doesn't matter. Just anything in a
What
vector
is this
map.
notation? N bracket? What is it?
This is the spinor helices.
Oh, the spinor
relation. So this is A,
Okay. Thank you.
A. Okay, so the way that we're going to do this is by using unitarity cuts and channelized unitarity. So, yeah, I'm just going to start. Okay, so when I say unitarity cuts, what I have in mind is that I'm doing some one loop integral. That one loop integral is of a one loop integrand, and mostly what we want to do is see what is the right integrand to construct. Okay. Now, the Karpowski theorem tells you that if you take a one loop integrand like this, and I do a unitarity cut, which means that I take some internal loop propagators and I put them on shell, then it needs to look like a product of two tree-level propagators at one loop. Now I can do this not just for a bubble. I can take a box integral and do 3 cuts, and it needs to look like product of 3 trees, or 4 cuts, it needs to look 4 trees, etc. Okay. And depending on which dimension you're in, these cuts will or will not be actual physical divergences in your amplitude. So if you're looking at 4 dimensions, the only cuts that actually give you a divergence are ones where these 3 amplitudes are non-vanishing in 4 dimensions, right? So if I want to construct my integrand, and all I'm using to fix that integrand is that on 4-dimensional cuts, I divide into 4-dimensional tree-level amplitudes. If that's what I'm using to fix my amplitude, fix my integrand, then I only get the divergent bit, right? Because I get the bit that actually has a divergence in 4 dimensions. So it's often called the cut constructible part of the amplitude. It's the part of the amplitude that has the log, it has the part of creation threshold.
So when you say divergence, you mean non-analyticity?
Yeah, a log type.
Yeah, right.
At one loop. So for these amplitudes over here, There's actually nothing, no tree that it can break into in 4 dimensions. So just because we already saw that the trees satisfy duality preservation, whatever you call it, helicity preservation. So these trees don't exist in that case, right? So these amplitudes are necessarily rational amplitudes. They're not going to have any 4D divergences.
What do you mean when you said 4D divergence?
I mean that you have something like a log. So basically, I generally have a branch plot and that is telling me that there's some 2-particle creation threshold, 3-particle creation threshold, something like that in my one loop amplitude.
What would a 3D divergence be?
3D divergence. No, I just mean that. So my external states are all in 4 dimensions.
Yeah.
Right? So now if I can break on a loop, if I can break into 2 4-dimensional tree amplitudes, then I know that the 4-dimensional loop contribution
But
has,
when you say 4-dimensional tree amplitude, why are you bothering specific dimension?
because
It cuts into 4D.
because if I allow these internal states to be d-dimensional,
Oh, so higher dimension.
not, I mean, when I say d, I usually mean like 4 minus 2 epsilon.
Okay.
So, because then that doesn't guarantee that it's going to give me a divergence, right? Because it's not a physical cut.
I see.
Yeah.
Right.
Yeah. So that's why I'm differentiating between a cut and a rational. And what I'm trying to say is that these duality non-preserving or duality breaking, the violating, the duality violating amplitudes are all rational. That's what I'm saying. So, and the way to get these rational bits can never be from just using 4-dimensional cuts. That's why I keep stressing 4-dimensional cuts. Yeah.
So, and just to continue with that, are you going to be using dimensional regularization?
Yeah.
And that's why you're saying that there may be trees in 4 minus epsilon dimensions,
Yeah.
but you don't care.
I'm emphasizing why that is the only thing I should care about. Because if I only cared about 4D trees, this would just be 0. And so actually the leading contribution is this bit. So normally if this is non-zero, you just have to calculate the bubble coefficient or something like that, and you're done. It's just a leading thing. That's
If what is non-zero?
the bubble coefficient. So okay, I mean, basically the cut constructible part of the amplitude. If that is non-zero, you're fine. That's the leading contribution when epsilon goes to 0. But now when epsilon goes to 0, that's going to be 0. So this is not.
But that's also like a path that you could change by adding a local counter term.
This. Yeah.
Yes.
Yes.
So,
But I guess that's the question. Can you change it by adding?
meaning,
Because this is just rational. It doesn't have to be local.
oh, I
So
see.
that's the question of whether symmetries are anomalous or not.
I see. Thank you.
So if you took some arbitrarily irrational epsilon,
Yeah.
A and one loop is just A, there's no irrational part of it, because you can always make it. Is it true that you can always make the internal exhaustion for some electron?
Exactly. So, yes. Generalized unitarity. So in generalized unitarity, you do exactly that. You're now breaking your amplitude into trees, but you're allowing the internal legs to be d-dimensional. And so then you don't have to think about rational pieces. What you would normally call rational would come from the fact that your legs inside are d-dimensional. So this is the same statement. I'm taking all of these propagators, I'm putting them on shell and getting a product of trees. I'm just allowing these trees to now be d-dimensional trees. So 4 minus 2 epsilon dimensional trees.
So I'm very confused about the whole chain. So you're in general in 4 minus epsilon dimensions, so whatever do.
My external states are all strictly in 4 dimensions. All the polarizations and all that strictly in 4
There and only the loop momenta are being regulated.
Yes.
Okay. Right, I see. Okay, and just to understand, I should have asked you earlier, if you were just writing down a tree level amplitude, just imposing that helicity constraint, which you call electromagnetic duality, landed you exactly on the DBI action. Is that correct?
At tree level.
At tree level. At tree level. Okay. And so.
Wait, sorry, say your question.
Okay, you showed that the DPI action gave rise to the helicity constraint, which you called electromagnetic. And does it go the other way around also? It doesn't go the other way around. Okay. So, all right. Thank you. Now coming here, is the basic chain of argument that you have the constructible part and then something else?
Yeah.
But that something else would have had to be a tree level amplitude in 4D anyway, which you've constrained? Is that?
It would if the symmetry is non-anomalous, which we don't know. So that's what we're trying to figure out. Can I actually remove such rational contribution by adding local content?
Okay, which symmetry is not? It's the electric.
The helicity conservation. This is the same, like, so if you were trying to figure out whether supersymmetry is violated at 1D, you would do the same thing. You would, let's say, calculate one of these amplitudes that you know have to vanish at 3 level. And then see, does it give a contribution? If it does, I need to subtract that with a contribution.
Thank you.
And just going back to question both Abhijit and Sandeep asked, you showed this sort of BCFW type recursion applies to your Born-Infeld.
Yeah. The duality value.
Yes. So then, doesn't that show that the Born-Infeld tree level amplitudes were completely determined just by the 4-point amplitude?
The duality violating amplitudes are determined to be zero.
But more generally,
we didn't say anything about the.
But why could you use the same argument?
Because at z equals 1, that doesn't match. So I can't do that subtraction.
Okay, thank you.
So you have to do something a little more involved, which is the supersymmetric software.
Thank you. You had two fields. You just have a 1 over z.
Exactly.
Not 1 over z.
Exactly.
Okay, thank you.
So what we want to do now is then construct the integrand in the following way, where I know what these trees have to be, or at least we figure out what the trees have to be, and then put them together, write down the integrand, integrate, see what I get. Is that something local? Is it not? That'll tell me whether I can preserve this symmetry or not. Okay.
So you just analytically continue the tree amplitudes to form minus epsilon dimensions.
Yeah, I mean, you have to be a bit careful because if you're dealing with vectors,
Yeah.
what is happening to the
polarization?
polarization. So the first thing we're going to do is not deal with vectors.
So superset.
Yeah.
Okay.
So normally you would, so as I said, you have this internal vector loop. But once you have a full supersymmetric theory, let's say n equals 1, you have a vector loop, a fermion loop. N equals 2, you have a vector loop, 2 fermion loops, and a scalar loop. Now you can think of these as Feynman diagrams, or you can just think of them as cuts, right? So this is the part that is given by the scalar cuts at 1. Okay. So
Sorry. First to ask you, I mean, in terms of preserving vector-like features and all, I mean, at least in my experience, which involves gauge fields and fermions, it's better to do dimensional reduction rather than regularization because you keep the number of components the same.
yeah.
Right? And then actually it sort of works pretty well.
Yeah, I agree. So I'm not saying there are no ways of doing it. Not at all saying that. I'm just saying if you can do it for scalars instead of vectors, it's better. Like life is just happier, I think. If you don't have to deal with too much tensor reduction, you still have to deal, but like much less. Okay. So basically you solve these equations like you would in 8th standard. So you would just say that you want to write this bi as the sum of these plus the scalar contribution. What are the coefficients sitting? These are the coefficients that have to sit. And basically this 2 will then cancel these two fermions with each other. This minus will cancel all the vectors. All you get is the scalar. That needs to be compensated. Okay. And because of this argument, basically what I'm saying is that these two helicity configurations vanish when I have any amount of supersymmetry. So for n equals 1, n equals 2, these two bits over here, they vanish. So all I get is the scalar contribution. So this one loop pi is just the scalar. Okay. So this whole problem has reduced to what are these scalar tree amplitudes. Once I know that, I can write down my integrand and I'm done. Well, almost. But okay. So
you just show the previous slide just once. So everything there, so
So
that,
vector, fermionics.
and so only that last part.
I look at the linear combination so that these bits vanish and all.
Oh,
So in terms of scalar, n equals 1 and n equals 2.
Yeah.
Just change basis.
Yeah.
And she knows that the n equals 1 and n equals 2 is 0.
Yeah.
oh, that's the.
That's
Why
the-
is that zero?
That's
Because of this.
Okay.
Oh, the original arrangement is an element known as Suzy theory.
yeah. You want to get the vector exchange.
Yeah.
Right. Thank you.
So, yeah, so as I said, all you get is the scalar, so all you need to know is the scalar cuts. So the scalar cuts are whatever you have external Born-Einstein photons and you have these internal scalars. And yeah, what is that amplitude? Now, when I say the scalar,
Does this trick work if the loop has a box shape? Because then you would have to worry about whether the vertical, if you're cutting this way, the vertical guy should be scalars, but directly. Scalars and the could be vectors, right?
Yeah.
How do you deal with that?
so you deal with it actually in a very basic way, very similar.
Oh, it's just, you can just still get
Yeah,
some
you
equations.
just you have more things,
Okay.
more of these pictures, but you can still do it. Yeah, because
Can
the
you do it
computation
like
then.
this?
No, you just do the one.
Okay.
One. Yeah, because that, yeah, no, I think it's enough to do. But this is a paper by, I think Byrne and Dixon, if I'm not wrong. But they do this for rectangles, which is actually a little simpler because you have color ordering and you have, you only have one vertex. I mean, you basically only have 3 or 4 point interactions. You don't have anything else. You can, yeah, which is much. It's a bit simpler that setup. Yeah. Okay. So the scalars are d-dimensional, meaning they're 4 minus 2 epsilon dimensional. So I can break up my loop momentum as being 4-dimensional bit minus 2 epsilon dimensional bit. The ways that the loop momentum enter the amplitude is the following. You can have some external, some Q dotted with L, which will only pick up L4, right? Because Q is in 4 dimensions. All external momenta are in 4 dimensions. The other type is L square, which looks like this, and I'm now going to call L square minus 2 epsilon mu square.
So I don't know what this split is for. Because this L equal to L4.
This is the part that is only in 4 dimensions. So like if I think of it as a vector, I'm just saying this is L4, this is L minus 2.
And the really nice thing about the scalar is that you didn't have to do something similar with the internal epsilon.
Exactly. No polarizations, all I have to think about is the momenta. And so also because of that, this mu square, all it's doing is changing the momentum. All it's saying is that these scalars are now massive scalars. And also as a result, I can just think of this as in 4 dimensions. So this is now a 4-dimensional amplitude with massive scalars. So that's all I need to construct a 4-dimensional amplitude with massive scalars and Born-Einstein photons, such that when the mass goes to 0, I get n equals 2. Why is that? Because that was exactly, in 4 dimensions, this will become an actual cut. And so this will have to contribute. And so I know that that needs to be, the trees need to be n equals to 2 Born-Einstein trees. Okay. So this is going to be the strategy. I don't know if we should embark on this strategy today or not. But okay, let me just quickly say what the strategy is. You want to write down this model with massive scalar Born-Einstein so that it reduces. You then put these trees together to construct an integrand so that you have the right ones and no extra cuts, no extra propagators in your integrand. Then finally, you do the integral, and obviously that result can't have any extra dimension full parameters, right? Because where would they come from in the actual BI amplitude? So you can't write down a model that has some other parameter in it. All the parameters of your tree-level amplitudes have to be fixed. Okay. Yeah, I don't know. Maybe let me just see where we get and then pick it up.
Sure, I have it now. Okay, you can go ahead.
Okay. Okay, so let me quickly just apply this condition. The fact that when mu goes to 0, I get this n equals to 2 theory. Okay. So the n equals 2 theory, I know what it is. I know the amplitudes in that theory. And so I know that, for example, this needs to be 0 for a very similar reason to this over here. This again needs to be 0, again for the same reason. So the only non-zero, let me just remind you that the amplitudes I'm interested in, they will have either all of these being pluses or all but one of them being pluses. So these are all such type of amplitudes in n equals to 2, and these have to vanish, whereas this is fixed to be this.
I'm really sorry, but I'm a bit confused.
Yeah.
I mean, the phi's and gammas, of course, denote the external states being scalars or
Right.
vectors. What is the 4 phi bar? The bar is what? Or what is that? I mean, pluses are the helicities of the vectors. What's that bar?
The bar is like simply a bookkeeping device to
Okay.
tell me, because in this n equals to 2 theory, it's a complex scale.
Okay.
Yeah.
So in a sense, okay, depending
So
on
when it
the
reduces,
external
yeah,
core.
yeah.
Okay. Thank you.
Okay, gammas are all external, right?
Gammas are all external, and so all of them have 44.
And why do you allow one helicity to be different also?
Because that will be, I'm going to look finally at two configurations, the one with all plus and all but one plus.
She wants to show all of those with zero. Well, I mean,
The all plus ones, yeah, and the plus with one minus. I want to look at both of them ultimately, and so
But is it true that only because you don't yet know whether it's the U1 symmetry is preserved or what?
yeah.
Yeah.
Okay.
So the question you're asking is, are these terms all rational? Are they polynomials or not?
No, they have to be polynomials.
I thought you said they have to
Because
be
they're
rational.
not, there's no cut constructible rings. They have to be rational. They don't have to be local.
So isn't that the difference between polynomials and rational?
No, because you can have poles as long as they're tree-like. So say I introduced a local counter term for the all plus. Then I can attach a regular tree to that all plus, and it will give me the all plus with one minus.
Right.
And that is a perfectly valid thing to find
That's
when you do a loop amplitude.
So that's something that you could eliminate by
Exactly, but it wouldn't look like a polynomial. It
I
would
see.
have poles.
I see.
Yeah.
Thank you. Because it could be just in some lower order, some diagram, you're saying.
Yeah, exactly. So, okay. So here, when I say that these vanish when mu square equals 0, that doesn't mean that I can't add something over here that is proportional to mu square. And that's sort of the whole question. What are these amplitudes with the mu square included? Because that is the epsilon bit, right? And remember, that is the part that's actually d-dimensional. This is just 4-dimensional. So, generally, as I wrote before, amplitude equals poles plus without poles. So, amplitude equals parts that factor and parts that are compact. Okay. And I think a natural place to stop will be fixing the tree level amplitudes, and then we can look at the loops. So, to do this, the first thing to do is just to figure out what is this power of mu square that sits out in front, what is allowed. And to do that, you just have to calculate the mass dimension of various things. So this is the mass dimension of the amplitude. This is the mass dimension of the Born-Feld coupling that we saw over here when Diksha asked her question. And then there is some power of mu, and then some kinematic part.
What was lambda?
Lambda is the Born-Feld coupling.
Ah.
So the kinematic part will include all of the wave functions as before. Here there are only n minus 2 vectors, so there's n minus 2, not n, like we saw, plus some derivatives. The question is, how many derivatives am I allowed? Now, for this equation to be true and a to be positive, because it needs to vanish when mu goes to 0, right? This is the only possibility. It has to be mu squared. And because it has to be mu squared, it has to be zero derivatives, which means it just has to be made out of these scalar brackets like this, with no extra momentum or anything like that. Now, there is no way of contracting this that is non-zero. Because n minus 1 contracted with itself is 0. So, there is literally no kinematic term you can write down at this mass dimension for these helicities. And here there is exactly one, if you have permutations. So now our problem is reduced to what is the coefficient sitting in front of this contact.
Sorry, I didn't understand that, so I'll just try.
Yeah.
So for the first statement,
Yeah.
so the left-hand side has one scalar, has
Two
how-
scalars.
Two
Yeah.
scalars, okay. And now you're saying that I want to write down an amplitude involving two scalars with a mu square.
With a mu square.
And naively, such a thing should exist because we have n f's.
Yeah.
But you're not stripping off two things for the polarizations for the scalars.
Yeah, exactly.
Therefore, mu square should exist.
Exactly.
Okay.
Yeah.
And then you said sometimes it does, sometimes it doesn't. Right?
Yeah, so in this, so it's not just nf's, it's nf pluses.
Okay.
But once you have nf pluses and one f minus, the f minus has nothing that it can contract.
Yes.
The f minus has nothing that it can contract into. So there's nothing it can do. It's just, I mean, it is, yeah.
Some index
Yeah.
of it. Okay.
Yeah, index of it. So the only thing you can have is this, and there's only one such thing once you have permutation symmetry. And so that's just.
Okay.
Yeah.
So that's the thing that can enter in the loop.
That's the thing that can enter, and we need to figure out what it is.
Okay.
Okay.
What is LSD? So the LSD is there.
Oh, sorry, next to self zero. That just means plus
I see.
plus this. This is MHV. Because it has, if you did it supersymmetrically, this would be MHV. That would be zero actually.
And this is not looking far away, but for mere models, what is the term in the Lagrangian you write down to get the
F plus to the n minus 2.
with two phi's, is it?
Yeah, so like 5
What is
squared.
mu? Mu is like some coefficient there or what? I didn't understand.
It's the momentum in
Mu
the
is, yeah,
other directions.
yeah, mu is this.
Mu is just, but in your 4D theory, it's a mass.
It's just a mass.
So-
Mass of the scale.
So what was the argument to use? What's the big concern with mu appearing? Are you just studying this and okay, sorry. You can always write it down like this, phi bar if you want.
See, the
Right, but you need it to vanish when mu square equals. So when mu square equals 0, it needs to look like the n equals to 2.
Is it? So just put a mu square in front.
See, dimensionally, the amplitude you're looking at have the dimension of f to the power n. Because it came from this body.
Yeah.
Okay, now I understand.
Now, if you had only vectors outside, each of the vectors has to come
With the derivative.
with the derivative.
Yeah.
So it pulls out all of those in.
Okay.
But now two of them don't have that.
Okay, now I
derivative.
understand.
So you can have.
I wasn't
Yeah.
able
Yeah.
Thank you.
Yeah. And if you added
Okay, it was
derivatives over
dimensional,
here,
yeah.
And if you added derivatives over here, you have to introduce a dimension full parameter, which you're not allowed to do because your final answer can't depend on anything other than the bonded term. Yeah. So this is the only thing.
Okay, thank you.
So
And what is capital lambda?
capital lambda is the bonded term.
Oh, okay.
I know it has not appeared before now, but
Yeah.
that's because I usually don't write it at all unless I have to.
Is it theta is square root that or is it itself square root? Is it like 1 plus lambda f or is lambda square root that?
It's 1 plus 1 over lambda to the 4.
F.
Yes. 1 over lambda square. Yes.
Wait, sorry.
Whatever, it needs to be dimensionless because it's added.
One is dimensionless.
One
That
is
much we can
dimensionless,
agree.
and so yeah. Lambda is dimension 1.
It's alpha prime. Square root alpha.
Ah, okay.
One also.
Lambda has dimension 1. And 1 has dimension 0. That's all we need to do. Yeah. Okay. Okay, good. So good. So now, as I said, if you look at an amplitude like this, the only thing that you could have is this, right? Because these are two pluses, And over here, you have a mu square, which is the only thing you could have, and a 2, 3 square contact. That's the only amplitude. Okay. This one over here is MHV, so it has no possible contact terms. So the only thing it is whatever it was for n equals 2. So what property can I place on these two that now fixes the value of C4? And the property we choose sort of goes back to our brain construction, where we saw that we had these two scales, that if you went to 3 dimensions, your Born-Infeld amplitude looked like you had these two scalars. And actually, if you look at the action that those scalars have, they actually have these very special softness, which is that they vanish at order p squared when I take p to 0. Okay. So basically here, if I take 1 to 0, then this would have been p1 squared. Sorry, if I took, say that again, this scalar is not the same as this scalar. Yeah. So if I take this scalar if I take the momentum of this scalar to 0, I get p squared.
Sorry,
So this scalar, one second, this scalar is the combination of gamma plus and gamma. So this you remember is what we did before. We had this picture with the D2 brane, and we said that this it had now one scalar modulus, and that scalar modulus has some special soft behavior, which is what I'm using up there, and this equals some linear combination of the gamma plus and gamma minus.
I'm just not understanding the structure of the argument.
Yeah.
You're trying to you're giving some physical argument for how
C4 is fixed.
how this amplitude with the scalar scales with momentum.
Yeah, so I want to fix C4 ultimately.
Yes.
And so I want to place some condition on these amplitudes so that I can fix C4.
Right.
And the one that I'm choosing is the fact that when I look at this linear combination of amplitudes with this gamma plus over here and gamma minus over there, and I go to 3 dimensions, then I'm actually this scalar modulus. And so I have some special soft behavior.
So this scalar here. Wait. So
It's a dBi scalar.
it's a dBi scalar. Nothing to do with this artificial scalar that you.
No, nothing to do with it. So this n-1 came from the photons. It didn't come from the scalar.
Okay.
Yeah. So it's gamma plus and gamma minus. That's why specifically over here. Okay, yeah, I should have used better notation. This phi might be different from this phi. I don't know if you can see.
Okay. Yes.
But yeah. So specifically, when I take n-1, p n-1 to 0, I get this.
I see. And why was it this combination that? Why wasn't it every amplitude that had the soft behavior because of Goldstone-like property of phi? Why this combination?
You just have to check what is the actual combination that gives you that.
Okay.
Yeah. I don't think there's a smart thing.
Fine. Thank you.
I mean, the phi, phi plus phi bar. No, sorry. This is phi 1, right? This is phi 1 and the other one is phi 2. Because the combination was phi and phi bar, which went with the
Yeah, exactly.
polarizations.
Yeah, so you know that it has to be some combination.
You're saying you pick out the one direction, which is one of the Cartesian directions.
Yeah.
Okay, thank you.
It's a complex one that goes.
So it's just putting it real.
Yeah.
You're saying just getting real.
Yeah.
Okay, thank you. Thank you. Yeah, that makes sense.
I think I called it X.
Okay, fine. Perfect.
So now I just say that this amplitude has to behave as P3 square when I take P3 0, because 3 is now the special thing. And so then that says C4 equals minus. That's the only combination. So, alright. So I can do this again at 6 point, I can keep doing this. And there's a general argument that I'm not going to give you, but basically, let's look at the 6 point.
Sorry, where did this artificial scalar go in this whole argument? Sorry.
This guy? These are they're just there. I mean,
they just said, how do you make a physical argument when the artificial scalar is lying there?
You have to think of then those scalars as also, you have to think of this whole MDBI model as coming from a dimensional reduction of BI from 6 dimensions to 4 dimensions.
Yes. In some
Already you've dimensionally reduced 6 to 4 and now you go 4 to 3.
Oh, fine.
Okay, so this all plus amplitude, I remind you that you can always write down these pole terms, right? The pole terms involve the other all plus ones, which was just mu squared 2 times 2 3 square with this coefficient minus 1. Okay, so you have this pole, this is the pole. And then you have this possible contact contribution. At MHV, you only have the pole terms, no contact contribution. Good. Now again, you do the same thing. You reduce to 3D, you take the soft limit, and then you find that C6 has to be 0. In fact, for all n greater than or equal to 6, Cn has to be 0. So this means that you have all your tree level amplitudes. The only ones you have are these over here. Everything else is just pole terms. Okay, so I'll stop really soon, I promise. I just wanted to show that these are the only tree amplitudes that exist. One is, these are the only tree level vertices that you need. The rest you can just join together and have pole terms. So you have
So
this.
you're saying subtraction with this will eliminate all those everything that you get from.
Yeah. Yeah. So like I can put this and this together and that will give me a higher order term, but I'm not writing that down because I can always do that. So yeah, so I have this plus amplitude, plus minus amplitude at 4 point, this 1 6 point contribution where I have this massless pole, and then the propagation. And so now all my other tree level amplitudes, I can put all of these together. And so
why do you stop at a particular number of points, the extreme number of points?
because so for the higher point amplitudes, first thing is that there are no more contact contributions, but also you'll notice that this particular amplitude has a massless pole. There's no mu square over here, and this is the only order at which this can happen. Basically, this is telling you that you can take these, and that will give you a Born and Feld all vector interaction. So you have to include that in this, and
What
then
happened to
every
the plus?
that won't have so that doesn't have any massless.
Okay.
So the rest can all be taken care of with scalar propagators. The only time you can't deal with the scalar propagators when you have this particular 6 point amplitude that has this non-scalar, one fermion, one vector, internal vector.
So before you explain why this is true, next slide please.
Oh, sorry.
What is the consequence of it? I mean, these poles are something we should worry about? Or?
No, it's just that I just want to write down all tree level amplitudes in this theory. And I'm saying that putting these together, if I treat these as, for lack of a better word, like Feynman rules,
You can make them all, I
I
understand.
can make them.
But now, if I wanted to understand whether the original theory had the symmetry that you wanted,
Yeah.
the
I
loop,
have to now construct the integrals.
well, you're going to do some subtraction, but including subtraction involving poles or not? Sorry, maybe I'm misunderstanding.
So I'm not sure what you mean by subtraction.
I thought you were going to change the theory by adding some local counter terms.
Yeah.
Okay, so that's what I'm calling subtraction.
So okay, good. So I will do that in the other. So I'll first calculate the loop amplitude and I'll see what I can add to
Okay.
do the subtraction.
Okay.
Yeah. Otherwise, I don't know what to subtract.
Okay.
So I don't know. Should I stop now?
I would suggest yes, because I'm
Okay.
teaching my unit actually.
Okay. Fair. Okay. I will give you a warning then that the next stop might be a little bit of this and then something else.
Yeah, we're really sorry for.
No. It's fine. This is just a warning to all. Yeah. Yeah. Okay. But I think.
You are going to say next question not allowed to decide.
No, please. This is good. I'm glad people are asking questions. I'm glad we're all on the same page. And yeah, I think we made some progress. So we got to the bits that now we can put together to get the integrand, and we put them together, we integrate, we figure out what is happening to the duality. I think that's a decent plan.
I don't know if there is anybody on Zoom, but if you can hear me, if the Zoom audience has any questions.
How do I don't know if I can see this. Oh no, I'm sharing screen, so there must be. Oh no, there's only one.
That's you. Okay.
Yeah.
Okay. the audience here.
There's been a lot of questions, but let me just go to your last slide because I couldn't. I thought the point was we're trying to decide whether there are any counter terms which were non-local, right? Which you couldn't subtract. That was the issue, right?
Yeah.
And the worry was that you get a term which has a mu square on top, but then it's divided by epsilon and right? So is the bottom line that now you have classified all the terms with due to the mu being non-zero, which can appear. You're going to put them together and then come to the question whether this.
Yeah.
Exactly. Okay.
She still has to do an integral.
I still have to do an integral. I
This
will
is just the integral.
not tell you how to do the integral.
Sew them together. Sew them together.
Do the integral, the one loop.
Yeah, you have to construct the integrand, do the integral, figure out what it gives you.
I thought these were just the parts which could appear which were not cut constructible. So you're just writing down 4-point functions in the theory with non-zero mu square. I mean,
Not
that's
just
not
4
true.
point, but
Okay, higher point because you want to do highers out of these.
Yeah. So, but you're just getting to find the integrand, right? Because you're just computing 3 diagrams in these.
Yeah.
Now you still have to do the integral over this.
yeah.
And then you get what you get.
Yeah, exactly. So this still involves the loop momentum, which obviously the final amplitude, on-loop amplitude doesn't. So, yeah. So, I mean, even mu square is a pre-integration
Yeah.
object. It doesn't make any sense in the amplitude.
And are you going to put us out of our suspense by telling us whether?
No.
No.
Then no one will come to the no. Okay, I can tell you. It works to an extent. It works in these 2 sectors, and beyond that, there are a few more assumptions you have to make for it to.
That's